Good morning, guys. All right, so guys, this is the start of a new unit, and the unit is called exponential functions. And guys, honestly, this is one of my favorite topics in the course, and the reason why I think it's one of my favorite is a lot of the stuff that we do in this course is it's very theoretical in the sense that it's leading towards calculus. But in terms of actual real life math, I think this is one of the most relevant things that we're going to talk about all year. No, this is the most relevant thing that we'll talk about all year. So, exponential functions is one of the big applications of this stuff is finance. So, I've kind of designed this topic, all the examples be having to do with kind of money like that, in finance and kind of interest like that, how you something called compound interest. So what we have over here is so the compound interest formula. Okay, now the compound interest formula is this guy over here, a equals p times 1 plus I to the n. So a is the accumulated amount of the investment, I is the interest rate per compounding period, and n is the number of compounding periods. So I'm going to do kind of a longer explanation on how this one works. So if we have 2,000, what we're going to multiply times is 1.12. Now, when we do that, I'm just going to do some with my calculator here. We get an answer of 2,240. Okay, so I'm going to put in brackets here. We have an increase of $240. So we started at 2,000, we ended with 2,240. This is just after year one. Okay, so I'm going to put after year one. Now in year two, we have 2,240, and we're earning 12% as well. So times 1.12 again. So go times 1.12, and we have 2508 and 80. This is dollars here. Now, hopefully what we're seeing over here is this is going to be an increase of 268.80. Okay. Now, what we're seeing here is that in the first year we made $240 in interest, but in the second year we made $268 of interest. Now, the reason why it's more is because we're earning interest on the amount that we've already earned as well. So we're earning interest on the principal, which is called the 2,000, the initial amount over here. But now we're also earning interest on the interest that we've already earned. So this is why it's called compound interest, okay? Because we're earning interest on the original investment, but then we're also earning interest on the interest that we've earned in previous years. So year three is going to be 2508.80 times 1.12 again, which is 2809, and I'm just going to round this one over here, 86. So the amount that we earned is an increase of 301.06. So again, in year three, we're earning even more interest. In year four, we have 2809, and guys, there's going to be a faster way to do this in a second here. 86 times 1.12, which is 3147.04, which is an increase of 337.18. And last one, we're going to have year 5, which is going to be 3147.04 times 1.12, which is 3524.68, which is an increase of So what I want you to know is that the amount that we're earning every year is actually getting bigger every year. Okay, so the idea is that, guys, when it comes down to it, this is how millionaires become billionaires and how non-millionaires become millionaires, right? So if you have like investments that just earn compounded interest over a long time, or if you keep contributing to an investment account and that amount comes investing over time, well, the idea is, well, when you have a job, if you can start investing a small amount away every month and that money is earning compound interest, well, that's how when you retire, at the end of working for 30 or 35 years, that's how hopefully you're going to have like a very big nest egg in your bank account like that, right? So it's like this is how people kind of retire, with over $1 million in the bank account, is because they're investing every month and that money is earning compound interest all the time. So the quick way to get this answer over here is using this formula. And guys, there's a variable I'm missing over here. P, which is this value right here, is what we call the principal investment, which is like how much you have to start with. Okay, so doing this question using our compound interest formula, our accumulated amount, which is going to be this value over here, the amount after your 5 years, is going to be, so we have A equals P, 1 plus I to the n. A equals, our principal amount is 2,000. It's 1 plus 0.12. So 12% as a decimal is 0.12, and we have 5 years. So I'm just going to plug this into my calculator, just the way we see over here. 2,000, 1 plus 0.12, exponent 5, and this gives us 3524.68. Okay, so this is going to be able to tell us how we go ahead and use this compound interest formula. Now, the topic of this one, guys, is called exponential functions. Now, really what an exponential function is, the variable in this equation, like this is going to be a constant value. I is going to be a constant value, but the variable value is going to be the time for the number of compounding periods. Now, I'll explain what the number of compounding periods means in a second, but this is really our time expression for this equation over here. So an exponential function is going to be a function that has the variable is in the exponent. Okay, so just a couple things over here. If we have this is a polynomial function, specifically a quadratic. Okay, it's because the variable is the base, but then the exponent is a constant over here. But if I have y equals 2 to the x, this is an exponential function. So they look similar enough, but the difference is on exponential functions, the exponent is the variable, whereas a polynomial, the exponent is a constant, and the base is going to be a variable over here. So compound interest can work against you as well. So this is like if you take out a loan that you owe in 4 years. Okay, now it's going to be compounded 6% monthly. Now what this means over here is if this is 6% monthly, this means 0.5% per month. Okay, now it does matter, okay, because, and the reason is because, like, if you're taking 6% per year once, that's not the same thing as taking 0.5% per month. Because if it's 0.5% per month, well, you get charged a bit of interest in the first month, but then you get charged interest on that interest in the second month, and the third month, and the fourth month, and so forth. So it does matter over here. So what we have over here for our A equals P1 plus I to the n is this is going to be our I. Okay, so our principal, the amount we're borrowing, Okay, it's going to be 5,000. And this is going to be 1 plus. Now, the way we got this 5% was going 6% divided by 12, because there's 12 months in a year, so 6% per year. This slash A means annually. But we're going to go 6% divided by 12 to get 0.5. So this is going to be like really 0.06 divided by 12, which is going to give us this 0.5% here. Now, our exponent, though, is 4 years, but we have 12 months per year. So that's going to be an exponent of 48. Okay, now I'm just going to plug this in my calculator just exactly the way I see it. So 5,000 bracket 1 plus 0.06 divided by 12, exponent 48. And this answer gives us 6,352.45. So guys, this is the unfortunate thing of having to finance things and borrow money is like if you borrow 5,000 and then you have to wait 4 years to pay it back, you're gonna have to pay back 6,352, right? So that means that the interest charged is actually 1,352.45. Okay, so that's a significant amount. So 6% per year compounded monthly ends up being like $1,352.45 that you're kind of paying back to the bank as kind of as a fee for borrowing this money. Okay, example 3. So these are just a whole bunch of just compound interest calculations we need to do here, where A equals P, 1 plus I to the n. So 10 years at 8% compounded semi-annually. So semi-annually means twice per year. So this means 8% divided by 2 is 4% per half year. So this is going to end up being A equals principal, which is $10,000, times 1 plus 0.08 over 2, 10 years, but it's going to be 10 times 2 because it's happening 2 semi-annual payments, of interest payments, times 10 years. So this is going to be a 20 in the numerator. So now it's just calculator time. 10,000, 1 plus 0.08 divided by 2, close your bracket, exponent 20 equals 21,911.23. Okay, so if you think about this, guys, a $10,000 investment would more than double over 10 years if you're earning 8% per year. 20% at 12% compounded weekly. So in this case, same formula. We have A equals our principal is 10,000. 1 plus, now weekly, because this should be common knowledge, but hopefully we know that there are 52 weeks in a year. So we're going to go 0.12, this is 12% as a decimal, divided by 52, and it's 20 years times 52 weeks in the exponent. So we have 10,000 divided by 1 plus 0.12 divided by 52, exponent 20 times 52. And this answer would be 109,927.40 cents. Okay, so we're going to round this one to 2 decimal places because it's money. Okay, so guys, 12%, 10,000 would become over 100,000. Okay, 35 years at 10% compounded quarterly. Now, quarterly means every quarter of a year, which really means 4 times per per year. So what we're going to do here is A equals 10,000. We have 1 plus 0.10 divided by 4, because it's happening 4 times per year. And we have 35 years times 4. We're going to fire this in our calculator. 10,000, 1 plus 0.10 divided by 4. Exponent 35 times 4. And this answer is 317,205.83. Okay. So, guys, I mean, I don't know if you've ever, like, the point I'm trying to make over this is the longer that your money sits in an investment account, you know, it can blow up. Have you ever heard the word old money like that, right? So this family has old money. Now, usually what they're referring to is like, you know, they had some relative, you know, some ancestor, you know, probably hundreds of years ago. Well, they understood this and they were able to, they had some money to begin with, but then they invested that money, and that investment essentially accumulated interest for decades, maybe even centuries like that. You know, it kind of keeps earning interest and earning interest. Right? And so that's how, like, you know, some of these big, huge, you know, billionaire families like that, you know, that's how they've made this money. Like that, right? So they invested the money, and then that money just grew and grew and grew and grew, and eventually, like that, you know, the point is like you want to be able to live off your interest like that, right? So when you want to retire like that, you want to have enough money in the bank that with the interest you're making, that just becomes your income like that. You know, that's how you kind of go into, that's how you retire like that, right? That's how you want to be able to do that. Okay, so just a huge advantage you can have in life if you can go and, like, the longer that your investment sits in an account, the more money you're going to have down the road. Okay, so the theory behind retirement planning is you're not taking big chunks like 10,000 investing at a time, but you're investing like, you know, like, I mean, maybe right now, guys, I know that some of you guys probably have jobs. You know, would it be unreasonable to say that you're investing $50 per month? Okay. Well, I mean, like, if you have a job, maybe that is, okay. And then when you graduate university, you get your first job, okay, you change that from $50 per month, okay, to say 150 or 200 per month, and then you get a few raises, and you start raising up to 500 per month. And then, you know, you become the vice president of the company you're working for, and you start investing like, you know, $2,000 per month. And that's how you kind of, at the end of your career, you know, you have, you know, millions of dollars that you're able to go leave to your kids or leave to your grandkids and stuff like that down the road. Okay, guys, this is going to be an example over here that I'm going to show you guys in class, but I'm not going to show you guys in the video right now because this is definitely kind of an extra topic like that, you know, that we don't really need to kind of talk about for this course. But in class, guys, I'll definitely show you how this one works. So over here, guys, we're just, I mean, so those examples are examples of what we call exponential growth, okay, and how these ones work. So just for example 5, this is like what we're going to call our base exponential function is 2 to the x. Okay, so what we're going to do is we're going to fill out this table of values and sketch a graph. So if x equals -2, this is going to be 2 to the -2. Now, review from our exponent rules, guys, from math 10. 2 to the -2 is the same thing as 1 over 2 squared, which is 1 over 4. Okay, so that means our first value is 1/4. 2 to the -1 is 1 over 2 to the 1, or 1 over 2, which is just 1/2. So this value is 1/2. 2 to the 0 equals 1. 2 to the 1 equals 2. Good. Sorry, guys. For a second, I thought my screen wasn't recording and just found that it is recording, since I can go back to what I was doing. That would have been really frustrating if I need to record all this stuff over again, but I think we're all good. Okay, so we have so 2 to the 1 equals 2. 2 squared equals 4. 2 cubed equals 8, and 2 to the 4th equals 16. So following this, so we have 4, 8, and 16. 2 to the negative 2 is 1/4. 2 to the negative 1 is a half. And this function just starts growing like this. So just, guys, there's a term which is thrown around all the time, which is that something is growing exponentially, okay? Mathematically, here's what that means, okay? What exponential means, if you start here at x equals 0, and I increase x by 1, my y value is being multiplied times 2, okay? So that's for this guy right here, my base is 2. So growing exponentially, if I increase x by 1, my y starts at 1 times 2 is 2. If I increase x by 1 again, 2 times 2 is 4. If I increase by 1 again, my x value by 1, 4 times 2 is 8. If I increase by 1 as well, I'm increasing 8 times 2 is 16. Okay, so the idea is every time you increase x by 1, we are multiplying times this base. Okay, so this is the base of our exponential function. The domain, this graph goes forever to the left and forever to the right. Our domain is from negative infinity to positive infinity. Now the thing about our range, like if I put in, say, a very small, say like a negative 1,000, this would be 1 over 2 to the 1,000. Now 2 to the 1,000 is going to be a massively big number, but 1 over that number is going to be a number extremely close to 0, but never actually equal to 0. Our range is going to be from 0 to infinity. So we talked about this a bit in, well, we talked about this in our trig unit for sure, and we talked about it in Math 20 as well. What we have here is y equals 0 is what we call a horizontal asymptote. So this is a line that as x approaches infinity, negative infinity, going to the left here, our function is approaching this line, but it's never actually going to cross it, okay? So y equals 0 is going to be the horizontal asymptote for a graph like this, and this is how our exponential function graph looks like. So in this case, this is another exponential function, but now we have a base of 1/3. So what that means is every time that we increase x by 1, we're multiplying our y values times 1/3, okay? So filling in this table of values, if I have 1/3 to the negative 2, we have to remember, guys, what does negative exponents do? They flip your base, the reciprocal of your base, and becomes positive 2. 3 squared is 9. 1/3 to the negative 1 is 3 over 1 to the 1, which is 3. 1/3 to the 0 is 1. 1/3 to the 1 is 1/3. 1/3 squared is 1/9. So the idea is every time we increase x by 1, so we're increasing x by 1 here, we're multiplying our y values times 1/3. So we get negative 2, 9, negative 1, 3, and our graph looks like this guy over here. Okay, we have y equals 0 is our horizontal asymptote. So this graph is approaching this guy over here. Our domain is from negative infinity to infinity. Our range is from 0 to infinity. Okay, so remember, guys, we are not including 0, so we have a round bracket here because this function will never equal 0 over here. Okay, and this is how this exponential function looks over here. Okay, guys. Guys, you've all had 12 years of social studies by this point. Hopefully you can answer this question. I'm going to give you my definition, guys. Mr. Barry may disagree with my answer in social, but what's inflation? is going to be the rate at which the price of an item changes over time. So guys, I don't know if you have grandparents who kind of say that, oh yeah, back in their day, like you go to a movie for like $1, like that, right? Well, obviously you can't. If you go to a Landmark these days, it costs like $15 to go to a movie, right? So the idea is things used to be cheaper back in the day, but then the price of things starts to increase. Okay, so what we have over here in this chart is that like year after year, like from 1998, so 1999, goods cost 2.63% more than they did the previous year, right? So if you look at this over here, this is the amount year after year that everything's changed. Okay, so I actually looked this up a few years ago. This is from a Government of Canada website over here, and this kind of talk about the inflation index for all these over here. So what I did was I just kind of took the average of all these numbers over here and said that the average rate of inflation from here to here is 1.8675. Okay. Now, the thing that's a little bit confusing about this, so if a Slurpee cost $1.75 in 1998, find the average annual rate, and the average annual rate of inflation is 1.8675. How much does Slurpee cost in 2017? Okay. Now, so from 1998 to 2017, this is 19 years later. Okay. So what we're finding is our price is increasing. Okay. Now on your formula sheet, we're going to see this formula over here. And this is our exponential growth, we put /decay formula. So what this means is this is the amount after time. This is the starting or the initial amount. This is the growth /decay factor. The T is time, and P, we'll cover more examples about P in a second here, but this is how long it takes for the growth factor to happen. Okay, we'll talk about this more in a second. So in this case, we're going to have y equals $1.75. Okay, now the tricky part is what's going to be our b value or our growth factor. Our growth factor is going to be 1 plus 0.01865. Okay, now the reason why it's 1 plus is because if I'm multiplying this through the brackets here, 175 times 1 is the original price of the Slurpee. 175 times 0.018675 is the amount that the Slurpee is increasing by. So if I want to figure out the new price, I need to be the original price, which is 1.75 times 1 here, plus the increase, which is going to be this part over here. This is going to be taken to the power of 19 for 19 years. So I'm just going to put this in my calculator, 1.75 bracket 1 plus 0.01865 exponent 19, and the price is $2.49. Okay, so guys, just following this, when I was in high school in 1998, a Slurpee cost about $1.75. You go to 7-Eleven now, this is pretty close to the price of, so I think this is almost like exactly the price of the same type of Slurpee as well. Okay, so just like the cost of goods kind of follows inflation. So what I put over here, they call the time value of money. Okay, now what I want to go over here. Suppose you had some money right now, and you just like there's an expression called you put it under a mattress, which means you save it, but it means you're saving it in a way that you're not earning any interest. So you're putting in a bank account that has either no interest or such a small interest rate that doesn't really matter. The point is, like, if you want to buy an object now, but then you hold on for the future, that same object is going to cost more money. Okay, so the money that you have right now is going to be worth less. It's going to be able to buy fewer things in the future. Okay, so if you don't invest your money, you're actually losing money because the money that you have won't be able to buy as much in the future. Okay, so when you're thinking about this, the interest you're earning in your bank account, that's great, but it has to be more than the rate of inflation. If it's not, you're actually going to be losing money over time, okay, because your money is worth less. Example 8, okay. Guys, I'm typo over here. This should be 19 years ago, not 20 years ago. So if a large double-double costs $1.98 today, and the average inflation rate is 1.8675, what would the cost of a double-double been 20 years ago? Okay, so double-double is a coffee, guys. If you don't know, it's 2 creams and 2 sugar. Delicious. So we're going to be using our y equals ab to the t over p. Now, guys, in this case, this is like 1.8675% per year. So that means our p-value is just going to be 1 right over here, but we'll talk about more examples later on. So what we're looking for is, we know $1.98 today, that's kind of our amount after time, because we're kind of working backwards. We want to figure out the initial amount 19 years ago. So our amount is 198 equals A. This is what we're looking for, which is the initial price. Our rate is going to be 1 plus 0.018675 exponent 19. Now what I'm going to do is I'm going to figure out what this part is on my calculator. So we have 1 plus 0.018675 exponent 19. This is 1.98 equals A times 1.4212723364. And guys, this does keep going on like this. So now to solve for A, I'm just going to divide by this amount over here. So divided by 1.42 dot dot dot. And the price equals $1.39. Okay, so it's just this is kind of a question like kind of finance, study of finance and stuff like that. This is kind of the type of question that you might come across over here. So example 9 says a company advertises that on average it takes 7 years for an investment to double. Assuming we believe it will take 7 years for the investment to double, if you invest $10,000, write an exponential equation that models this situation. So we already talked about this formula over here. So in this case, our amount is going to be, our initial amount is 10,000. Our b value is going to be 2. Because if we say it's going to double, that means we're multiplying times 2. That's what our growth factor is going to be. And then we have t over 7. Okay. Now the reason why I'm saying is, why is it t over 7? Because if t equals 7, that means I have 7 over 7. That means my amount is doubling once. If t equals 14, 14 divided by 7 is 2. That means we're doubling twice. If t equals 35, 35 divided by 7 is 5. That means my amount is doubling 5 times. Okay, so this can be our equation. For part B, how much would you expect to have in 20 years? So, or sorry, 10 years. So we're just going to plug a 10 into t. So this is going to be y equals 10,000. 2 to the 10 over 7 equals 26,918. How long until it takes your investment to grow to 160,000? So in this case, this is our Y value. Okay, now this is kind of leading into what we're doing in topic 7.3, which is called exponential equations. But here's how this guy works. I'm going to divide by 10,000 here. 160 divided by 10 is 16, equals 2 to the t over 7. Now here's the way we solve this. This number was chosen carefully because 16 is actually a power of 2. 16 is the same thing as 2 to the power of 4 equals 2 to the t over 7. Okay. Now the idea behind exponential equations, if these two expressions are equal and they both have the same base of 2, this means that their exponents are actually equal. So we multiply both sides by 7 now. We get an answer of 28 years equals t. Okay, so this is how we kind of just do this. So this is kind of more kind of exponential growth financial planning questions. All right, guys, I don't know if you guys are old enough to ever remember there used to be a company called Blockbuster, and this is where we used to rent movies at the movie store. Okay, now obviously, guys, since stuff like streaming of movies became a thing, essentially renting movies at a store became a totally obsolete thing, right? So put this little chart over here. This is kind of the stock price of what happened to Blockbuster over the years. It just tanked. Okay, and it just Netflix went up, Blockbuster went down, and this could have what happened. So in this case over here, they're saying suppose the company lost half of its value every 2 years. How much would this investment be worth in 2018? So from 1998 to 2018, this would be 20 years. Okay. We're still using our y equals ab to the t over p. So we want y equals 10,000. Now in this case, our base is going to be half. Okay, so if it lost half its value, that means it's worth half of what it was every 2 years. Okay, and so we have our exponent's going to be 20 over 2. Okay, so it takes 2 years for this to happen. So time is 20. So in other words, 20 divided by 2 is 10. It's halved its value 10 times over that time. So I'm just going to fire this into my calculator, see how much you'd have left if you decided to invest in Blockbuster in 1998. And guys, this would be absolutely terrible if you did invest your money, but that means $10,000 would shrink down to $9.77 after that time. Okay, so that'll be obviously a terrible investment. Had you made that investment and kept it in that stock for that amount of time, it'd be worth $9.77, which is pretty sad. Example 11. Suppose Darko wants to buy a sweet new flat screen for his dorm room next year. He buys it for $1,000 on his Visa card. Visa charges an interest rate of 19.9% per year, compounded daily. And guys, this is what Visa does charge if you get a credit card. If it takes 3 months, which can be 91 days, we'll say, before he pays off his purchase, how much will he need to pay back? So again, this is how a credit card works. This is really just another compound interest question. A equals P 1 plus I to the n. And guys, you can see that 19.9% per year is a ridiculously high interest rate. Okay, so guys, buying things on your credit card, there is something what's called grace period, which if you pay off your credit card fully within 30 days of using it, they actually charge you no interest. Okay, but if you wait 31 days to pay it back, they charge you interest from the day you buy it. Okay, so it's 30 days for free, but then on day 31, that would be the same as charging 31 days worth of interest. Okay, so in this case, it takes 3 months before he pays off his Visa card. So we're applying this. So again, this is really just kind of an application of our compound or of our exponential growth formula over here. Our principal is 1,000. 1 plus 0.199. So this is 19.9%, but we're going to divide this by 365 because it's happening compounded daily, and there's 365 days per year. So put a little note here. Okay, now our exponent in this case is going to be 91 because it's taking 91 days. So this is the same thing as 1,000 times 1 plus 0.199 divided by 365, exponent of 91. So this is going to be So this is going to be 1,050.85. Okay, so the amount of so he would have to pay back 1,050.85 if he paid it back. Okay, so again, guys, I mean, this is only after 3 months. So Visa has made $50, and really, guys, I mean, like, Visa's making $50 just by lending you the money for a while, but they're charging you a very, very high interest rate over here. So he'd need to pay back 1,050.85. Okay, and so, but obviously, guys, the longer that you have to wait to pay off your credit card, just the interest starts racking up and racking up and racking up, right? And so it just guys, people go bankrupt because their credit card balances get too high. This is only off a $1,000 purchase, right? Like, imagine if you had, $30,000 on credit cards and you were taking years to pay that stuff off, right? And that's really, guys, unfortunately, that's how people go bankrupt, and it's awful when that happens. So, guys, it was a bit of a longer lesson over here, but hopefully you can kind of see some of the value of what we call exponential growth and how this works for questions like this. Definitely, guys, work on the questions in the textbook. You're going to need to go and really practice up on some of these type of questions, and I will see you in the next video.